Hello everyone, welcome to week 12 of these tutorials. So we'll wait for a few minutes and wait for some people to join and we can start. Okay, so I guess no more people will be joining. So this week the two topics were covered. First one is encoder decoder type of uh, architectures, and then we looked at the attention mechanism. So the attention mechanism is basically a way to improve this encoder decoder type of models that we saw. So if you have any questions, you can unmute yourself, or if you want to uh, write it down in the chat, you can do that. By the way, did anyone try to implement any of the algorithms you have seen in the previous classes? Yeah, am I audible? Can anyone please? Uh,
Yes, you are audible.
okay. So the topics that were covered in this during this week, it was mostly about how to use the architectures. So in earlier lectures, you have seen how to construct different architectures. Like you have seen how to use CNN for images, how to use RNNs for sequences, and also, yeah, those are the two types of architectures you saw. And also, yeah, you saw looked at encoders and autoencoders, right? To do better representation learning, how to represent your whatever data that you have and use it for downstream tasks, whether for classification or regression. So the most important applications that are that people use with the help of deep learning are these translation tasks or this generation task, right? You must have used ChatGPT. So ChatGPT is you ask a question to ChatGPT and they output some relevant answer for that. So that is not as easy as the RNNs or the text generation examples that you must have seen in the class. But on a high level, the idea is same. You give in some input, it defines a probability distribution over all the outputs, and then outputs you the most likely answer that you want. So the first encoder decoder type of uh, architecture that was shown in the class was the, I think, text generation, right? Yeah, any
I
questions?
have yeah,
Yeah,
a question like so in autoencoder also we were having encoding and decoding and
yeah,
then
right.
and these encoder decoder models also have encoding and decoding. So like uh,
Hmm.
is it similar?
Okay, so that's a good question. Let me join from my tab. Okay, so the question is what is the similarity or what are the differences between encoder and autoencoders or this encoder decoder type architectures, right? So if you remember in autoencoders, our task was to learn a good representation of the input, right? So how did you do that? You had some input data, say X, which you assume that we have a vector. Then you use some neural network layers or deep, I mean hidden neurons to encode it to some latent space. And this was your encoding part, and this was your decoding part. And then you want to get back the same X, right? So in a sense, you want this architecture assured that if you give an input and you learn some hidden representation about the input, you learn some information about the input. So this is the learning, the representation part. And now, how do I evaluate that the representation that I have learned is a good representation? You can just randomly say that my data is equal to some vector, but that does not make sense, right? You have to say that, okay, the representation that I have learned or that the network have learned is a good representation. And by good representation, we want that we can reconstruct the input from the hidden representation. So this decoder part wanted to reconstruct the input. So these are the autoencoders. But now, when you're talking about this encoder decoder type models, or architectures, let's say, we have that. So the task earlier was that you have some input and you have some output, and you design a neural network for this, right? Design a simple neural network for this. But now what we want is that our output, so this output, if it was say classification or regression, then it was easy. Classification or regression, you can just say that okay, this is my text, and whether this text is positive or negative, so that is what I want. But if you have some sequence to sequence type of input, let us say you have a sentence here. Okay, let us say you have a question here and you have answer, question and answer. You cannot use a simple neural network architecture, right? So because suppose your question is you ask a question like, let me say, tell me about today's weather. So that is a simple question. Tell me about today's weather. So the answer can will not be so if it was a classification, it will just say whether it is a one word type of answer, it is a cat, dog, or something. But when I ask something like tell me about today's weather, it should generate some text, right? It will say that today the weather is good. Today the weather is good. Uh, it will rain sometime and so on. It will rain in the afternoon and so on. It will generate some text. So how do we design a neural network while going from this to this? So for that case, so in this case, when you're talking about simple neural networks, our task was that given the input, you learn something about the input so that it helps you to tell something about the input. So if I pass a cat image, it will learn that it is a cat image and output that okay, it is a cat. But now you given the input, you also want to know what is the meaning of the input. So tell me about today's weather. So your neural network should know that okay, if it is asking me to talk about today's weather, I should generate text which is related to today's weather, right? So it should understand this information that you want information about the today's weather. So how do
So,
you make
yeah, so like in a way you are saying that autoencoder just did the task of learning the input and then reproducing it. But
huh,
these encoder decoder models, they are giving the context of the input also.
right.
Yeah.
So it will give you the context as well as it should understand your the meaning of your input. So
And then
what you do?
they can make prediction also based on that.
Yeah, right. So it will learn some encoding of the input, and then using this encoding, it will try to generate some text. So that is the decoding part. So you learn some encoding of the input, and you decode or whatever encoding you learn, you decode it and generate some output. So autoencoders was basically just learning the encoding of the input, but now given the input, you also have to produce the output. So that is a difference between autoencoders and encoder-decoder type architectures. So this encoding and decoding can be anything. Anything in the sense it will depend on what type of input data that you have. So like in the videos, you must have seen that the input can be a text, output can be a text, or the input can be an image, the output can be a text, or any combination that you want. Okay, so there is
Yeah,
a
even
good,
like
okay.
input can be video also. So
Yes.
we have to like for all these encoder decoder models that are given in the video lectures, like
Uh,
uh, like we need to like what is the basic thing about them that we need to know?
mm,
We have to learn about each one, like what was the parameter used, what was the loss function, what was the algorithm used,
mm.
or
So
like
the
we should just have the basic understanding, or we need to learn this.
so you should have a basic understanding because if someone gives you a very general task, so in the class I think five or six applications are shown, but it can be used for millions of tasks, right? So someone may say that I have some text data, so I am speaking in English, and I want you to design a translation system that types out my speech into say Hindi. So because my input is not text, but my output is now text. Uh, so you have to first encode the speech data in using some encoding type of architecture and generate some encoding of the speech data. And now once you have the speech data, you have to use this encoding to decode the speech data into text. So the basic idea should be clear. So you may not know what are some good neural networks for speech data. Even I do not know, but you may find out that okay, there is a neural network that takes some speech data and does something with it. So for encoding, what we do is, so suppose for example I'm talking about speech data. Anyway, I'm not an expert on speech data, so I won't say much. So for suppose there is a neural network which classifies your speech data. Say it it gives you an output of what type, what language your output is, what is the language, what is the language of the speech.
And then how the role of attention comes here in these models, like it's weight only, na? Like type of weight, attention.
So okay, I'll come to that. So yeah, so you have the speech as an input, right? And now you have some layers here. Maybe you have some RNN layers, maybe you have some CNN layers. I don't know how speech is processed. And then you have some output, say output of it will be a softmax output, right? Because there are limited number of languages and you need a probability distribution of this and so on. So this is a simple neural network for classifying speeches. But now I say that I need an encoding of this speech. So what we'll do is, so this is the last output layer. I'll just say I'll take the encodings here. I'll not go to the last layer. I'll just say I whatever vectors I get in this at this point, I'll take it out, and then I'll use this part as my encoder. So this part becomes my encoder, and I'll use this. So suppose I have some encoding key here. I'll pass this key to this decoder, which may be another say RNN, and then output a translation, output some translated text of it. So this type of application was not, so we saw some similar application where you have text to text translation, but I say that okay, my input is now speech. So the basic flow remains same, right? You have some network for speech detection or speech classification. you take out some encoding of it. So that part becomes your encoder part of the architecture. You pass on that architecture or you pass on that encoding to the decoder part of the architecture and then you get back this. So the basic flow should be clear to you, whatever application you are working
Yeah, so
on. And
this
coming,
initial part is an RNN before softmax that you are showing.
it may be RNN. So I am not familiar with speech. I'm just giving an example.
Yeah,
It may be
yeah.
RNN
Just
or
as an example,
ha ha.
this is an RNN. Then the softmax function is being applied, and then
Yes.
this encoder is also a neural network, and decoder is also a neural network.
Yes. So this encoder X is actually this part. The part that
Okay,
you get
okay.
after removing this softmax, that is the encoder itself. So you can take this part, or you may be interested in taking only this part, that is the encodings only here. So it's up to you. You have to test it out which part gives the best encoding.
And then decoder is another neural network.
So decoder will be, because this is a text in this case, it will be another RNN, or yeah, mostly it will be RNNs only because you are generating sequential type of information.
Okay.
So this is the basic
Thank
flow. Okay. So coming back to attention. Okay. So suppose, so I'll give you two popular examples that are used with NLP people. Uh, so suppose uh, okay, I have a sentence here. I have a sentence that he is going to the bank. It is situated near the river bank. So suppose I have some sentence like this. So the actual sentence is not uh, in this way. So the one thing I want to show is that the word bank. So this bank can have different meaning, right? So suppose now I have a question. Where is he going? So I have this question. So now you should uh, answer that. Okay, he is going to the bank. By this bank you mean the bank where you have money. Or now the question is uh, where is it situated? Where is it situated? And now the answer will also be bank, but now it will mean that it is the river bank. So the bank of a river. So actually the example is a bit different than this, but the essence is same. So what I want to show here is that depending on the question, so when I said where is he going, so all this information, where is he going? So this information is not really important to you. You are just on to the network. It will just say that, okay, you are looking at going in the context of going, the where answer is given by this bank. But when I said that where is it situated, so in the context of the word situated, the answer is bank. Now both of these banks are as spelling is same, but the thing is the network should know which thing you're talking about, which word should be given more importance to. So when it is looking at this as an input, when it is looking at whole this thing as an input, uh, this thing for the first question, this part does not make much of a difference. So that is, you don't have to pay much attention for this question. But for the second question, this part does not make any uh, it is not so important for this question. So the network, we want the network to look at or attend to only a part of the input that you have. So that thing is covered by attention. So attention basically is a mechanism where it tell or the network learns which, given the context that you have at the current time, which part of the input is more important at this stage. So for this question, this part is more important, and so it will attend to these two words. These things will have high attention scores. And if I am at this question, it will attend to this part of the sentence, and it will look at this and this word. So there's those things, those words will have more attention score in that case. So the attention, basically, you don't have to look at all of these, or the network does not have to look at all of the input sequences that you have. It will just give a score to each of the sequence and only look at the sequences which are most important for the current context that they have. And by the current context, I mean that the st minus one state vector that they have, it will only look at the uh, most important part of the inputs in that case. Is that clear?
Yes, so another confusion I have is like, so this attention, it's supervised, like we tell the network, or it's learned by the network itself, like it's unsupervised.
So the attention is unsupervised. You do not say anything because if you look, go back to the equations that were given in the class. So for learning the attention, there were a few parameters that were introduced. I think some UW or something like that. Let me check. So I'm just taking some snap from the this one. It was something like this. So you must have seen some equation of this sort. So what it was trying to say is that at time step t, uh, okay, at time step t, what is the attention on, okay, so this was 850. Hmm. At time step t, what is the importance of the word j, right? So like you are looking at this bank. So in this question, when it when it looks at this word going, the importance of this part will importance of this part will be high. The importance of these things will be small because those are not related. So it is given by this. So here this, and then we do a softmax of this term, and then we give some attention scores. So here you can see that these things, this u, this w, this v, those are basically learnable parameters. So that means once you train the network, it will learn these weights, this v, w, and u, such that the important parts, so that at this stage, say for this question, the network should learn that this thing is important. So for bank, these things will have some high weights, and for these non-important parts, it will learn that okay, these things have low weights at this step. So the attention is a small neural network because you have some weights times input, some weight type input, one non-linearity and another weight. So it is a simple neural network that you have, but it is not supervised. You do not say which things to give more attention. So it will learn by itself. So this part is important or this part is important. Am I clear?
Yes, thank you.
Okay, any more questions? So there's a message in the
After this,
chat. Okay. Oh,
yeah, this equation that you have written for attention weight, like
hmm.
after this, there is one parameter alpha also. So what
Yes.
is that alpha?
Okay, let me show you. So whenever you are writing down any attention, so we wanted these things are normalized. Normalized in the sense that uh, so it may happen that this EJT may be very large for some, maybe 100 or 1 billion. I mean, very large numbers, and for some it may be very small numbers. But we want generally in practice we want that everything should be between say 0 1. So if something is close to 0, we just say uh, there's low attention score, and if something is very high, close to 1, we say that it's large attention score. So we have to normalize this. So what we do is once we have this EJT, we perform a soft we perform a softmax over it. So if you remember softmax, so softmax was basically exp of e to the power jt um, by summation for all j exp of not j. Let me see what this is. I EIT. So this is basically EJT is your current word that you're interested in, and this is the and this part is summation over all the words in your vocabulary. So now this gives us a number between 0 and 1, right? And this gives us a number between 0 and 1, and we say that okay, this is the softmax score of this. So basically, we are saying that which what is the score of each word, what is the importance of each word. So that is given by this softmax function or this attention function, and when you use the softmax for making it lie between 0 and 1.
Uh, yeah, but like attention is a neural network, and
Yes.
alpha is the probability of the attention that will be.
So alpha JT is the uh, you can think of it as importance, not I not say probability, importance of word J at time t. So like for this question, the important word was bank. For this question, the important word was this bank, not that bank. So this alpha JT gives us this, because after this we calculate this context vector, which is basically a weighted sum of this, which says that how much weight am I giving to each word. So if some word has small weight, so that will be reflected here. If some word has large weight, it will also be reflected here. So yeah, the attention gives these weights. So which are more important, which words are not important, and so on.
So the equation of attention doesn't include alpha. Attention weight is used for calculating alpha.
The attention, yeah. So these are the weights. These are the learnable parameters. So these things are learned during back propagation through time. And once you have this, so for certain time step, you will have one value of U, V, and W. You'll get some EJT and you get some alpha JT. In the next time step, this U, W, and V will change due to back propagation. And now your EJT will change, and due to this, your alpha will change. So over time, your network will learn which words are more important, which words are less important. Initially, it will not know, but over time, it will learn.
Okay, so alpha is the output of attention, sort of.
Yeah, you can say yes. Alpha is the output of your attention. So you can think of it as a small neural network. You have some, say, ST minus one. You have which is a current or previous step, and some encoding forward edge J. Now you pass it through a network. So let us say we have some network like this, and your weights here are U attention. Here your weights are W attention, and now you use your non-linearity here, which is 10H, and you get something. And now you have a V attention weight here, and then you get back this EJT value. So this is you can say that this is your attention, a small type of attention network that you have.
Very basic machine learning question. Like,
Mhm.
what is the difference in normalization and standardization? So this
Okay,
softmax functioning is being used for normalization.
normalization. So whenever we talk about normalization, so whenever we're uh, yeah, whatever task we do, we want that our numbers are manageable, right? We don't want very large numbers, we don't want very small numbers. So it is generally preferred that our numbers are between 0 and 1. So numbers lie between 0 and 1. So then we use this term called
This
normalization.
normalization, is it related to normal distribution of stats?
No, 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 no.
Okay.
So normalization is basically whatever, suppose we have some numbers, so here 100, here 30, here 0.1, suppose you have these three numbers, and so these three are they have very different ranges, right? So this is very big, this is somewhat okay, this is very small, and I say that no, I want to write these numbers in within 0 and 1. So what I'll do is I'll divide this by 100 plus 30 plus 0.1. I will divide this by 100 plus 30 plus 0.1. And similarly, I'll do this. And I will get some number. I don't know what I'll get. I will get some number between. So because now the denominator, you see, denominator is bigger than this. So this will be less than 1. This is bigger than this. This will be less than 1. And also this will be less than 1. And also these are positive. So these numbers are also greater than 0, greater than 0, greater than 0. So my initial vector was this 100, 30, and 0.1. But now, after I do this normalization step, that is, I divide by the sum of these numbers, my numbers will lie between 0 and 1 in this case. So this step is called normalization. It's fine, right?
Yes, and
Okay.
standardization is also the same.
No, so standardization is a bit different. So suppose, mm, so suppose your data set is like this. You have So I am say looking at the features. I have age, I have height, I have weight, and I have say income. So your age will be in the range of say 10 to 90 or 100 maybe. Your height will be in the range of say 150 to, how tall are people? I don't know, maybe 250 centimeters. Again, weight maybe may to be between 50 to 200 kilograms, and income maybe between 10 lakhs to 50 lakhs maybe. So suppose you have some features of a data set whose ranges are like this. So if you're doing some sort of learning, you see that these numbers are very large, right? This income will be very large, but these numbers are very small. This thing is very small, and you want that okay, these things should not affect the output just because it is large. Because it is large, a small change in this will cause a huge change in whatever output we have. So we want that, okay, I want all of these to lie within certain range. So let me say again, let me say I do a normalization. So what I'll do is I'll make this lie between 0 and 1. I'll make this lie between 0 and 1, between 0 and 1, and between 0 and 1. So this is a normalization step. So now the values are comparable, right? So this will be say something 0 0.6, 0 0.3, and something. So now the values become comparable. In standardization, what we want is that, so suppose I have a 2D data and my data set is something like this, something like this. So now I cannot say any, so it will be easier if have if I move this data to this point here. So like I have the, so why this is good is because now I can say that my features will have a mean 0. So this is 0 0. This is the mean. So here your this mean was non-zero. It will have something, say let's say it is like 10 and 20, and this spread or the variance is also some large quantity, maybe say I don't know, maybe 100 or something, just. But when I standardize, now my mean becomes 0. That is, my data becomes more centered, it looks good, and my variance also becomes 1. So why we need this is because uh, in machine learning, if we make something to be a normal distribution, and make something to be a Gaussian distribution, it becomes very easy to analyze, and the models also start behaving better because Gaussian distributions have some special properties due to which it works better when your data is say, distributed normally. So what we do is we subtract.
Yeah, so
Hmm,
so standardization is related to normal distribution and normalization is not related to normal distribution.
no, 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 no. So in standardization, we just change the means and such that your total mean of each feature becomes 0, and the variance of each feature becomes 1. So that is standardization. So these are actually important pre-processing steps whenever you are running a machine learning code. So these are some of the basic steps that you should perform on your data to get good results.
Yeah, so as far as I remember, there is one standard scalar in sklearn
Right.
preprocessing which is used for standardization, and then there is this min-max
And now,
scalar which is used
ah,
for normalization. But uh, that I know that they are used, but the basic concept why we need to standardize and why we need to normalize and in what situation we need to normalize and in what situation we need to standardize that thing.
okay. So, so standardization is the most popular step that people do because, like I said, we want to make our data look like Gaussian distributions because then it becomes better. So we do standardizations in that case. For normalization, So suppose you are doing, you may be aware there are some algorithms called clustering or nearest neighbors.
Yes, yes.
Hmm. So whenever you are doing clustering or nearest neighbors, we don't want that some vectors are arbitrarily large and it affect the quality of your cluster or the nearest neighbors. We want that all of them are of the same norm so that we can calculate the whatever things we want in a better way. So then it is better to use say normalization. So it may also sometimes you also have to try out different pre-processing steps which help you. So depends on the data that you have. But generally these are the type of things that people do.
So ultimately, both of them are like setting our data within a certain range
Right. We want our data to be within certain
so that
range.
they can be compared. They can be
Right, right.
compared easily.
Yeah. We
Okay.
need to make our data look good so that it becomes easier for the machine learning or deep learning algorithm to work on it.
So the basic purpose of both is same, but the application is different. Like how do we decide? Like one example you gave is like for clustering, we need to normalize,
Right.
and so we can't standardize in clustering.
So you can also standardize here because it will not lose out on the data. So generally, it so happens that from my experience, what I've seen is that I run some code, but I'm not getting some good results. So I use a different type of pre-processing. Say, suppose I was using normalization earlier, so now I'll say I use min max scaling, and now it may happen that okay, it works good. So because we don't, because the data are very high dimensional, right? You have 10, 20, 100 dimensional data, and you cannot visualize it. So trying out these different standardization techniques, one may be a good way than the other based on the data that you have, and that works well for the algorithm that you have.
So it's experimental.
Yeah, it's experimental. But standardization is the most popular step, especially if you are working with regression models. Standardization always helps. That is what I found.
Okay. So
And even
standardization for regression and
yeah, so
normalization may be used for classification.
yeah, clustering or even
Okay.
classification maybe. So
So
if you are talking about
there's no defined line as such. It's all experimental. We have to try and see.
yeah, that is a type of tuning that you have to do. Which thing works
Okay.
better
There's
because
no
you cannot look
there is
at.
no defined thing like in regression you always have to use standardization
No,
and
no, no.
for like, okay.
So from my experience, I have seen that okay, standardization works well for regression, but maybe someone gives me a data set where this does not apply, so that may be a problem. So there is no fixed technique that we can do here.
Okay. And another thing, the regularization.
Okay, so regularization is a slightly different thing. So in the course, we covered dropout regularization, but I'll just say, so suppose, let me, what example? Hmm. So suppose I have many features. Suppose I have 10 features in my data set, right? And now suppose my weight vector W is also of 10 dimensions. That is, it assigns one weight to each of these features. But now what happens is if it assigns a high weight to each of these vectors, or it may be that out of these 10 features, it assigns a very high weight, say 20 to the first feature, 50 to the second feature, and it will not assign large weights to the smaller features. the rest of the features say. So it it may lead to overfitting. Why overfitting? Because it the data that you have seen, it may be that for those data points, these two features were most important. But the test data that you have, these two features may not be important. For the test data, these two features might have been important. We don't know. So we don't want the algorithm to only give high weights only to some of the features. We want them to give no, small weights to each of these features. That is, we don't want these values to be high. We want these values to be small. Say, uh, I will say that my first importance of my first feature is say 0.5, a second is 0.3, third is 0.9, and so on. So that means we want to regularize. We want to say that only I don't want to overfit to the data that I have seen. So maybe for the training data, only the first two features are important, but I don't want my model to overfit to the training data. I don't want them to memorize the training data. I want to make it more general. Say for when for test data, it should, even if the first two features are not high, you should perform well even for the test data. So the technique for doing this is called regularization. So it is a technique for preventing overfitting. So if you are writing a neural
So
network in
the
PyTorch,
confusion in regularization was that in regularization, not in here deep learning, but in machine learning, again in the regularization, the terms used are L1 norm, L2 norm.
right?
So again, like it gives a hint of normalization norm because they are
Oh no,
using
no,
norms.
that norm does not mean normalization. The word itself is norm. So norm and normalization are two different things. The word norm is another word itself. So it basically says you have some vector x, say x1, x2, xd, and if I say I want to take the L2 norm of x, let us say this. So it is basically x1 square plus xt square. Summation of squares of all this term and the square root. And if I say I want to take the L1 norm of x, it is just x1 plus x2 plus xt. So norm is, you can say it is a proxy for the length of the vector, how long your vector is. So that is what norm is. But normalization is something else.
So here, these norm are taken to regularize the weights.
Norms are taken to regularize the weights, right? So if we have looked at regularized loss functions, so that means whenever you use regularization, you will see something like this: minimize over W. You have some loss function, so that may be, this may be your mean squared error type of loss function, and then you will have something like W lambda times W2 square. So what it says is, I want to minimize this whole quantity, right? Now, if I want to minimize this thing has to be small, or this thing has to be minimum, and now this thing will also have to be minimum, right? Now let us say what W. So suppose my W is W1, W2 up to WT, and now I can say my W2 square is this quantity, right? W1 square plus W2 square plus and so on up to WT square. So I want these to be small. So okay, my loss will be minimized. Fine. And I want these to be small. So if this is to be small, this sum has to be small, right? And now if this sum has to be small, and these are all positive numbers, so each of these W i's have to be small, each wi square have to be small, right? So now if you connect it to the example that I showed before, so if wi's are small, so this whole thing is minimized. So now you look at this difference. This was some unregularized weight which have some high w's, and here the w's are small because we had regularization here. So that is the effect of regularization. It controls the type of weights that are learned.
Okay,
So this
and
is
this regularization is only for overfitting, or does it prevent underfitting also?
no, this is just to prevent overfitting. So you can always solve this underfitting by minimizing your loss, give it more data, give it run it for more iterations maybe. But there is you cannot do that for overfitting. For overfitting, you have to control the weight vectors that you have. So in
Okay.
PyTorch, if you are writing or creating a neural network, if you have seen there is something called weight decay. So weight decay basically is the value of this lambda that you have. So this is lambda that you have. If this is large, this thing will have to be small. So this W1, W2 will be very small. If this thing is small, then these W1, W2s may be a bit large. So that if you're if you code in PyTorch and you call something like say optim.sgd. So if you look at the options, there will be some option called weight decay. So you have to set the value manually. And once you give a weight decay, so the neural network will try to learn it will try to minimize the L2 regularized loss for your problem that you have.
So now this term came optimization. So optimization here optim. So it's the same as regularization.
No, no. Optimization is so minimizing the loss function.
Okay.
Optimization refers to minimizing the loss.
So optimization is a part of regularization.
No, regularization is a part of optimization. So the loss, when I say the loss, so this is my loss now. So one that I wrote here. So this is my loss that you have, and I want to optimize this loss. And when I say I want to optimize this loss, that means I want to minimize this term. So this term, and this is a regularized loss in this case. This is a regularized loss. If I don't have this term, don't have this. If I don't have this, it is an unregularized loss. If I have this, I have a regularized loss term, and we want to optimize it. That means we have to minimize it.
I lost you in the last sentence. You said last.
So this is a regularized loss because I have this
Okay.
regularization term. So this is a regularized loss. If I don't have that, only LW. So this is an unregularized loss. So in your models, it is always good to have regularized losses because it is very helpful for preventing overfitting.
This lambda W2 is the regularized loss, or after this
This
plus term,
whole thing.
the output will be regularized loss.
This part is the regularizer.
Okay.
So these are just terms. You just have to understand the concept behind this.
So this whole regularization that is being done,
Hmm.
this will lead to optimization.
It will not lead to optimization. Optimization is something that we do. So whenever we're using, say, gradient descent or stochastic gradient descent or ADAM, that means those are optimization algorithms. So suppose I am using, say, ADAM for optimization. It will take as input a loss function. Input is a loss function. So this loss function may be regularized or unregularized. And then this algorithm will output the optimal parameters or learned parameters. So this is your optimization algorithm. So this is the process that you have. So this could be Adam, or this could be gradient descent, or this could be SGD, or any of the algorithms like ADA grade or RMS prop, any of those things. So those are optimization algorithms.
This gradient descent or any other form of gradient descent like Adam, these we are using during back propagation for learning.
So these we are no, these we are doing after back propagation. So the general process is this. So let me say that I have a neural network training. So first I give the input, then I do a feed forward. Feed forward is basically you take your input from input layer to the output layer, and then it will compute the loss function by comparing with two output.
And here in feed forward comes the role of activation and function.
Yes, right.
Okay.
So compare prediction with truth value, compute the loss. Now you back propagate. So that means you compute the gradients of the loss with respect to all parameters. Compute the gradients. Once you have the gradients, now you apply optimization algorithm, and then you repeat again. So here, yeah, here you have these multiply with weights, and then activation function and so on. So if you have some spatial network, you can also have this convolution or this recurrent type of thing at this stage. So after once you apply optimization, the weights are updated. Weights are updated here. So this applies to all the weights. The normal feed forward weights, attention weights are updated, attention weights, the convolution filters, all of these things are updated during this optimization algorithms, convolution filters, and so on. So when you compute the gradient of all of these things, and then you apply, and then you repeat this whole process until you are satisfied.
Like in back propagation, we are just computing the gradient and later we are doing gradient descent. That is
Yes,
optimized.
yes, right.
Okay. And during optimization, then after optimization, I mean, then we are regularizing or uh, not regularizing as per the loss function.
So the regularization, so that has to be given as input. So you have to, during input, you'll have to say what type of loss you are using. So there itself, you can say that, okay, my loss function looks like this, where it may be regularized or not non-regularized. So you have to mention it beforehand. Before you start the training, you want to say what type of loss you are using. Maybe MSE, mean squared error, or cross entropy, or mean squared error with regularization. So that thing has to be mentioned beforehand, before you start training the algorithm. So if you look at some of the codes, so you will find that there is this thing called criterion. So that is the loss function that we give in PyTorch at least. You have to mention what type of loss function you are giving.
So in the beginning, we are defining the loss function in the beginning itself.
Yes, right.
And activation function
So
we define
activation,
later.
so activation function is basically your ReLU or sigma, right? So you define that
Yeah.
whenever you are creating the neural network architecture. So there itself. So suppose I say I have a convolution layer, and then I have a ReLU layer, and then again I will have a convolution, or then I have a ReLU, then I will have a pooling, then I have a fully connected network, then the output layer. So suppose this is my architecture. So I whatever whatever activation function I want to use, I will mention that during the definition of the architecture itself.
Okay, so activation functions are these also na softmax or logistic or linear.
So softmax is not an activation function. Some people may use it, but it is not actually an activation function. It it is just used to define a probability distribution over the outputs that you have. So yeah, logistic is an activation function, but softmax is not an activation function. You just use it at the last output layer to give you a probability distribution.
Okay, so it is an output activation function.
Uh, yeah, yeah, you can term it like that. Yeah. Any more
So you
questions
are
from?
saying, so you
Yeah,
are
go on.
saying like generally at every step in a neural network, we'll have a activation function at almost every step, but that may be some other activation function like ReLU or logistic or any other function which gives non-linearity, or linear function may also be there in cases of regression.
Right.
But softmax is generally in the last step only. It's not used initially.
Yeah, no, it is just at the last.
Like even in classification problems, like multi-class classification.
Hmm. So then, because it is a multi-class classification, you need to know which class your output belongs to with high probability, right? So then you will use softmax, because if it says that it belongs to class A with high probability, you will just output the maximum of those probabilities as your class. So then you will use a softmax there.
So in case of probability outputs, we have softmax as the output activation, and
Yes.
the loss function is generally cross entropy.
Right.
But in RNN, there was a assignment question. So in RNN, they said generally it is the sum of cross entropies.
Hmm.
So what is like so cross entropy and sum of cross entropy? Like what's the difference?
So if you remember RNNs, your RNNs were something like this, right? Uh, so at across different timestamps, you have some word here, uh, you have some neural network here, and you have some output here, some hidden state, say, and then you will have another state here. You have some word, say O1 here. Suppose I'm predicting the next sequence, and so on. And at sorry, 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 two, this is two, and say at time step t, I have WT, and it will output some OT. So my output is not just OT. So because this is actually a single neural network, right? I'm just writing it as so this is actually something like this. You have some input, some output, and you have some state given here. So the output is not just OT. My output is actually O1, O2, OT. So, but this we have some loss at this at time t1, some loss at time t2, and some loss at time t. So I want that this total loss should be minimized. So the loss at this plus the loss at this plus the loss at this should be minimized. And now we know that at each point the loss is a cross entropy loss, because we are just outputting a probability over the different vocabulary or size of the vocabulary that we have. So the total loss that you have to minimize is the sum of the cross entropy loss across all of these time. So that is what we want to minimize, the total loss across all the time steps for a given input.
Okay, so actually it was multiple choice, and there was the option of cross entropy also, and
Hmm.
sum of cross entropy also. So how do we know that what they mean? Like they mean the total loss, or they mean the loss we are using at every step?
So I think for a given input, so my input now is not actually W1. My input is this whole thing is my one. This is the input that you have. So because this is the input that I have, I will have different outputs at different time steps. So my loss function will be sum of cross entropies.
Okay. Okay, so it's not single, and then total. It's actually the total only.
You accumulate the loss for all the time steps, and at the last step you add it up. and you want to minimize that.
Okay. And the output activation functions, like for probability, it will be softmax, but for
Softmax.
real outputs, real value output, it can be linear or tan.
Then you don't have to do anything. We don't need 10x. So if you're talking about regression, so whatever y you output at the last layer, so that itself you compare it with the uh, true value that you have, and you just say the loss is a mean squared error loss, y minus y hat whole square.
And
So
the
don't have to apply
activation will
anything.
be linear only. It means linear activation.
Yes, we can say that. Yeah. So there is no really any activation, but yeah, in a sense, it is a linear activation.
Okay. And then while you were talking of attention, you
Hmm.
said that it is incremented based on the probability. It is incremented at every time step. It changes at every time step.
Yes, right.
So then, what is this concept of hierarchical attention? Then a normal
Oh,
attention is also
hmm. So hierarchical attention is, so there is a hierarchy. So in the class, the example that was given was you have some words and you have some sentences, and based on that, you there is a, I think, classification task, whether it is a political message or not, something like that. So
mm,
now, whether if you want to say that some sentence is political, you have to look at certain sentences, right? So suppose you have a sentence, this is an apple, so that is not a political message. But if you have another sentence, say, what, he is a criminal, so that is obviously a political message. So now your network should learn to give attention only to that sentence, because I mean not only to that sentence, to give a high attention to that sentence, because that implies that he's a politician or something like that. So that is a sentence level attention. But now, if we go to the sentence, how did we know that that sentence is important? Because that sentence has the word criminal in it. So I'm not saying all politicians are criminal, but we don't know. So anyway, so when we go to that sentence that he is a criminal, it should attend to that word criminal. So that criminal should have a high attention. So now you see there are two levels of attention. One attention is for the word level, criminal should have a highest attention, and then another attention is at the sentence level. So there is a hierarchy of attention. So that is the hierarchical attention that was being mentioned.
gave that bank example for attention. There
Hmm.
also it's sort of hierarchical only, na? Like it's giving the word level as well as sentence level.
You, it is a sort of yeah. The example that I give, it is a sort of that hierarchical attention. But the context here was a question answering. So in terms of the question, which word is in attending to, you can say it is a type of hierarchical attention.
So for hierarchical attention, we need to understand only this concept, like it's at two levels, word level and sentence level. And normal attention is only at word level.
Yeah, when you're talking about text generation or question answering, generally it is at word level, because we give a context. Say, I'm I want my network to generate a certain word, but I also give it a context. Like, I have seen this text, what should be the next word? or what should be the translation for it. So it will only attend on some words for that. So yeah, it depends. Actually, it depends on the application, but generally I have seen that yeah, it is used only for word level attentions.
And attention itself is a neural network in itself.
Attention itself is a neural network. Yes.
And for attention over images, there is a separate topic. So that is attention in CNN, I believe. Um, is it different in some sense, or it's the same concept? Hello.
Yeah. Hello. I.
Um, yeah, I was saying so attention over images is the same concept just applied on CNN, or is there any other difference?
Oh, so attention over images. So whenever we're talking about attention over sequences, like in sentences, so we're looking at the important uh, parts in the sequence. So important, let us say, words in the context. So for sequences, it is like whatever words we have seen beforehand, say at time t minus 1 or t minus 2 and so on. But for attention over images, so these are so this is an attention over locations in the image. So if you, yeah, in the class, there was an example which said uh, a man is throwing this. So the man should attend, or it should give importance to the image of the man. The disk should give importance to the disk in the image. So these are the two difference. So in images, sorry, in sequences, you just give attention to the words that you have seen and which you think are most important for, or which the network thinks are the most important for the next output. In images, you or the network learns which part of the images are causing it to give certain output. The concept is same, that you have a small neural network that learns weights according to the different locations or different positions over time, but the way it is implemented is a bit different.
Also, like this is our last class, or we'll be having another class.
So I filled up the form for an extra session next week this time. So I think it will be announced. Yeah, it will be announced in a few days. So that will be a open session in the sense that you can ask any doubts
Okay.
there.
So that will be next week.
Next week. Yeah.
Okay, thank you.
Thank you. Yeah. Any more doubts on this? Where this week's topic or anything before this?
Just a small thing. So in hierarchical attention, there was this term utterance. Utterance.
Let me check. So can you give me the timestamp if you have it?
I think it was at the very beginning. So they were saying like each utterance has a sequence of words, and there is a sequence of utterances.
Okay. So utterance, okay, sequence of utterances.
Each utterance has a sequence of words. Each utterance has a sequence of words, and there is a sequence of utterances. So it seems
Oh,
like utterance is a sentence.
yeah. So there is, so in this image, you can see there are three sentences, right? Can, you, movie, wish, your, look, and so on. So okay, okay. So they're talking about chatbots. So in chatbots, you so even if you have worked with ChatGPT, you give a question, the chatbot will return an answer. Then when you give a question or you say something, to reply something. So each of these is an utterance that you have. So the question that you give is an utterance. The answer that the chatbot gives is an utterance. So like in this example, there are three utterances, and each utterance is a sequence of words that you have. So can you movie is an utterance. Yes, sure, Logan is an utterance and so on. There is a question in the chat, how to score high marks in deep learning. So if you have went, if you have gone through the uh, this assignment well, if you go through the questions well, and also the lecture videos, try to work out the examples yourself, then I think it should be fine in that case. I'm not sure what the type of questions will be, but it will be of the same form.
So in the class we'll be having next week, can you like give us an overview, like yeah, you won't be knowing the questions that will be coming, but like some important questions that may be asked that way.
Okay, so yeah, I don't know the question, but I can just point out maybe the type of questions that may come.
Yeah,
So hmm,
so there are some such questions because it will be most likely multiple choice. So
hmm,
they give some sort of questions in which we are confused in two options or something. So
hmm.
that sort of questions.
Yeah, I will try to go through the assignments and yeah, let me see what I can come up with. Yeah, I'll try to do that. Meanwhile, if you have some doubts about previous
Yeah,
distance
yeah, that we
assignment, you can
ask.
also bring it. Yeah.
Thank you.
Okay.
Uh, it's a very general question, not related to any specific topic. But there is this concept of linearity and non-linearity which has come in different places during deep learning. So,
Mhm.
what exactly is that? And like by introducing these sigmoid functions, we are introducing non-linearity. Why are we doing that? Like,
Okay.
yeah.
So that's a good question. So for that, let me give you an example. Wait a minute. So if you remember your first few classes, I think there was this example of XOR, right? So XOR was this function. We have 2 points here and we have 2 points here. And your task was to learn a decision boundary so that it learns something like this. So everything inside this is say positive, everything inside outside this is negative. So now if you from your high school, if you remember the equation of a line, what is the equation of a line? Say y equal to mx plus c. So that means anything also, let us forget about c for now. Let us say we have y equal to mx. So that means anything that can be written as y equal to something times x is a line. So in terms of machine learning or neural network, suppose you have y equal to, you learn some parameters w and some x. So that means this is a line, right? So this is a line in this sense. This is a line of this sum, right? So now, if you look at this example, I cannot draw a line such that I can say that the points on. So suppose I draw a line something like this. I cannot say that these things are positive, these things are negative, or I cannot draw something like this and say that these things are positive, these things are negative. That means this XOR problem cannot be classified or cannot be separated using a linear decision boundary. So cannot be classified using a linear boundary or a linear function. A linear boundary or a linear function. Right? So that is why we went to neural networks. So what was the advantage of neural networks? The advantage of neural networks was that we had this concept called non-linearity. So what exactly, so if you remember how we applied non-linearity, we perform, we give given some input x, we multiplied it with some weight w, and then we applied say sigmoid or ReLU or 10h or any such thing to wx. So now we say that okay, this is a non-linear function. So when we talk about linearity, anything that can be written is a matrix. So this is a matrix and this is a vector. So these things are called non-linear. These things are called linear. So by linear, we can think of that this is some form of a line. But if you have some function of this wx, so that is non-linear. And we saw that using this nonlinear function, the neural network was actually able to learn these type of boundaries. So if you have linear boundary, we will have something like the line. But now we see that these things are not line, right? These things are say some curved space type of things. So this is a nonlinear decision boundary. So using this nonlinearity like sigmoid, or sorry, logistic or ReLU or 10H, it enables us to learn these type of things. So that is the
so
basic
that
difference
so
between
that
these.
we can do better predictions, better the classification.
Yes, for this complicated type of things, it is better to use this nonlinear type of boundaries.
Okay. And then in linear also there is a term linear and independent.
Mhm.
Independent, like this came in that lecture of eigenvalue, eigenvector, PCA, where the basis is defined as a linear and independent vector. When
So,
we are going towards non-linearity, this independence criteria is not a must, or there also it's there.
so there, this thing does not. These things are not defined. These may be defined,
Okay.
but I am not from a maths background. So I am not aware. So I'm only aware of this linear independence. So let me say I have a line, and suppose I have a point here, say 1, 2. I have another point here, say 2, 4. Another point here, say 3, 6. And I have another. So this is actually these are the location of the points. And I have another line. Let me say this is what is this? Say 2, 1. So if I write it down in the form of a matrix, what do I have? I have, I can write it in any order. So write like say I write 1, 2, 1, 1, 2, 4, 3, 6. So here you see these 3 points. These 3 points lie on the same line, right? So I can write this. So suppose uh, Suppose this is my point A, so I can write this point as 2 times point A. I can write this thing as 3 times point A, right? And we have some other point B. So I can write it as I have some point B, I have some point A, 2A, 3A. So these, if I change A, if from 1 to, I say my A is something else. Suppose I say that my A is 1 comma 3 in this case. So my 2A and 3A will also be different. So if my A is this is my A. So my 2A will be something like this and 3A will be something like this. So these 2 points, it depends on what we have for A here, right? So that means these 2 points are not independent. These 2 points are linearly dependent on A. Because changing A, we will get a different set of points for the last two, 2A and 3A that we have. On the other hand, if I change A, instead of A, I say I write A equal to 1 comma 3, this point B does not change. This is linearly independent of A, right? So that is the concept of dependence, linear dependence and independence. If I change a point, if the other points does not depend on this, so that means these are linearly independent, else they are linearly dependent. Is this clear?
Yes, yes. Thank you very much.
Mhm.
Many concepts have been cleared like during your classes and today also. Thank you.
Right. Thank you. So if there are no more questions, maybe we'll again meet again next week.
One last question. Like you
Yeah.
explained this linear independence. So, so for a basis, which they had defined a basis
Mhm.
for eigen. This,
Yeah.
yeah. So a basis has two conditions. What I understood, one is that the vector should be linearly independent, that you
Right.
explained,
Mm.
and the other is like every vector in the space Rn can be expressed as a linear combination of these vectors.
Yeah.
This
So
linear
taking
combination.
uh, so taking this example, so when I draw this x and y axis, so actually this is the basis that I have. So any vector in this, so suppose I have some x here, some y here. So if I draw any vector, this or this or this, so these vectors can be written as a combination of this x-axis and this y-axis, right? So even for matrices, that is the case. So suppose my basis vectors are say 1 0 and 0 1. Let me say that this 1 0 is x and 0 1 is y. So this is x and this is y. And now if I have any vector 2D vector, say let me say 3 comma 5, let me say. So I can write this as a combination of x and y. So this is x something times x times y. So I can just write it as 3 times x plus 5 times y. So this thing is a linear combination of the basis vectors this and this. So that is what we mean by saying that any vector can be written as a linear combination of basis vectors. There can be other basis vectors also. So here I wrote 1 comma 1. So suppose I have another something like this, say, and something which is orthogonal, perpendicular to this. Say this is AB and this is CD. So these two things should be orthogonal to each other. And if they are orthogonal, that means they cannot be linearly dependent, right? Because changing this will not change this. So now any vector, say 3, 5, can also be written
So,
as
so,
some
uh, so bases are always orthogonal to each other.
bases are always orthogonal to each other. They are linearly independent from each other. So this vector 3, 5, if if I say that if AB and CD are basis vectors, so then this can be written as some constant times AB and some constant times CD. Because these are basis vectors, any vector in this two-dimensional space can be written as a linear combination of these basis vectors.
Okay, so there can be multiple basis vectors
Yes, there
in
can be
a,
multiple basis vectors.
and then they have defined some time complexity also.
Uh,
Means they have gone into very much mathematics. I don't know how much is needed.
so time complexity won't be asked, I think, because
Okay,
hmm,
okay. So
so that
I
is a
think
bit involved.
they were creating the ground of why PCA is needed using these things.
Okay. So time complexity is basically I think ND square or something, but so that means the how much time you need for computing the matrix vector multiplication. But that may not be, I mean, since he was teaching it in a class, probably that may not be required.
To matrix. Yeah, this mathematics related to matrix was asked in assignments like calculating the eigenvalues, calculating the eigenvectors, and then
Hmm.
uh, yeah, covariance and all those things, like they are actually like they are conceptual only, na, like, or they are not actually used while implementing deep learning, right?
Oh, yeah, no. So if you are coding it up, those things are already implemented in Python. You don't have to write it up, code it up.
Okay, this is
But
just
for
for
understanding,
giving us the background.
yeah, right. It helps for better understanding of these concepts.
Yeah, but like for people who don't have a maths background, this is something.
Yeah, for them. So even so in our institute also we are offered courses on linear algebra. So then it becomes a bit easier to do this if you are especially involved in this type of research. But other than that, if you are in an applied field or you're just looking to apply these algorithms, those things, okay, it's good to understand it, but it's not really necessary. All of these things are already implemented in Python in different libraries.
Okay. But from exam point of view for this course, like such questions will be coming because they are giving similar questions in assignment.
Okay, if you
It's
are able to,
expected.
if you're able to solve the assignment questions, then I think it should not be that tough because uh, it will just be a computation question like compute the eigenvalue or so. So if you have any doubts, you can, yeah, you can go over this question in the next class. You can just make a note if you have any doubts.
Okay. Thank you. Thank you.
Yeah. Okay, so thank you for attending to this session. We'll meet again next week.